What class I don't like, I didn't say anything. I literally said it was not. Where's the thing? Oh, where's not the plaza? Where's
Okay, cool. We're back, and tomorrow we'll submit our first like real Jupyter kind of Python computational mechanics work. I guess one thing that that has come up a couple of times, and I help people here and there, but questions that I've heard already are, let me pull this up. Is like how to actually submit the homework. Loading, maybe. Launch. Oh, I'm not logged in, that's why. We're back and logging in, but the main thing that I was going to show, it'll take a second to log in, but create a print preview of that homework notebook, and then save that as a PDF, and that's the easiest way to like get. So here, CompMech 01, coming down to homework 1. And right now I have nothing done, but I'm gonna submit it anyway. So if you say download as PDF, you're gonna hit an error. Like 9 times out of 10, you'll get a 500 error. So don't use that download button. Hit the preview. Now you've got like a static web page of all of your work, and in my case, no work, and then Control P or Apple P if you're on Mac, but Command P creates that like option to print and save as PDF. Yeah. No, it just whatever is there, that's what gets put into that print preview. Yeah, so it's not gonna like run everything and then show you the one by one. Yeah. So that was the first thing that I wanted to show, was just when you're trying to submit this, file, print preview, save as PDF. What else? Anything else that people are working on? Anything more interesting than like how to save a homework assignment? IEEE specifications and underlying assumptions in numerical methods. Is the computer sentient? Is it trying to deliberately sabotage me with all these error messages? Yeah.
That population file, and then
Yeah.
I have a hard time with my graph.
With the graph?
You can just go over it again.
Yeah. So we're coming all the way down into like part three of the homework. So there's a couple of things that are, oh, I don't need all that. There are a couple of things that are just put there already. So in that the load text line in this np.load text, this is just how you get, oh, not that one. That's how you can get a CSV file. Like it's a comma separated value file. It's common output for like Excel kind of stuff, but like big tables full of things. And there's just a couple of values there. So we can take a look at that because it turns into year and pop. So plot year POP, and let's put that as like squares. And you know what? Let's give it a label since we're getting so advanced with our plotting and numerical methods. Oh, and I should run everything, right? Restart run all. And then it'll catch up with me in a second. So the measured population are just these kind of data points, like 1900, 1950, 2000, 2020. Just a couple of things. And roughly we could say like, yeah, that's some kind of exponential growth. So if we know the growth rate, then we should be able to predict, like make some kind of prediction on the population, like extrapolate to 2020 or 2030. At this point, 2025 is months away, but maybe 2030. A lot of times the analytical one is where people so I've got dp over dt equals k times p. And the solution for this, like the exact solution to this differential equation, is that p as a function of time is equal to p0 e to the kt. So like, but I don't have the population at year 0. I have the population at the year 1900. So that's what I want to use as like my year 0. So I'm going to say like population of 1900, and what is it, 1.6 billion, something like that? Yeah, 1.6 billion. So I'll call it like 1.6, which is going to be this P0 e to the k times t minus 1900. Just to make my life a little easier, like shift this whole function as if like e to the t is e to the t minus 1900. So now p of t is that 1.6 e9. We can add that e9, right? So I want to take that function and compare it to these measured values. Let's put in a new one. Time I can define however I want. Let's just make a linspace from 1900 to 2020. And I'll call my analytical one that pop of 0. So the first population times this exponent of kg. And did I define it yet? I don't think so. And now I've got like the exact solution to dPdt equals Kp plotted on top of that, like the actual measured values of the populations, reported populations. That's usually the analytical, because a lot of times people just plug in e to the k times t. And then it kind of looks like this, as if like the population is 10 to the 20, like in the, what is that? 10, 100, wait, 10 to the 20, what is that? It's so big, that's such a big population. We'd need like skyscrapers through the farmlands to like house everybody at that point. But orders of magnitude higher, because this is assuming that population at year 0 was the population in 1900. So all those people kept populating the earth for the next 1900 years to get to this one, like 10 to the 20 people. A lot of people. So we don't want to do that. We just want to leave it as 1900, t minus 1900 shifted over. That help with plotting, or was it also like integrating, like how to get the, is anyone having trouble, like what is Euler's method, or is that, I think we went over that a little bit last class, is that right, on Monday? But these are the other two comparison plots to see, is Euler's method getting towards either measured values or analytical values? All right, I was giving an awkward pause. I'll check in, see what people are working on, and then see where we can go from here. In a range, that's by start, stop, stack. Yeah.
It just wants you to like have like a. So you guys hate development, right? For the first one. So yeah. If business wants to do that for every single point, yeah, pretty much. And then for you do?
What's your project?
Yeah. It's a really big one. Oh, I know. I was in You're in South Korea. So I was gonna say, they'll remember. Oh, no, I know what you're going for. It's fun. The business thing right now. I got a little later. Then you know you can do it. It doesn't matter. Steps of. Like right now, I only see some items. See how its population changes.
I've been doing each, so do I don't just do it each time.
When you decrease the time step, the Euler's method, what is the Euler's method? Do you understand? It's just an approximation of what? The previous, the actual function.
Yeah, it's really, it's just running this function, and then just like makes it change over time, basically.
It changes over time?
Well, like, you're adding on the next portion of time, and so that step is the amount of time you're kind of calculating the population change. So like, if you have it as a bigger step, it'll have a worse, like,
Yeah, the smaller the step, it gets closer to the end.
Yeah, I know. But if you think of it as like,
call it a large
I'm at the year 1900. And what is
No, he didn't.
20 years? If you decrease the end, so
Doesn't convert to the actual population because
time,
population is a model time and actual
population I plus
Say that?
so like the sun is happening now.
I thought small for a week over there. I forgot when more.
Yeah, okay.
The only thing we're all
There's a way to put it.
Yeah.
Everything I can figure out about the year high.
You started to see one or two. I'm looking at the better words though. I'm like a darker word.
Yeah. So now if you change like 10 and 20 for that DT, like right now it's 10, change it back to 20.
DT is a
Yeah. Yeah.
Yeah, those are like the story that I'm working on. So those can't find that out right now. I like in the years ago. I mean,
And then this one is.
Like, I just took my two values from the previous, like the 2 times from previous times, and then I this is still Halloween.
Do I see in the free fall exam?
It's in
I see that.
I know I could definitely use some sort of loop to start. But I'll figure out smaller sets.
Yeah, and like one, I've seen like one person take
There's a major set.
Yeah.
Go up.
Number of times a day, so smaller times that.
Yeah.
Yeah, green and red, yeah. Yeah, and like really small. That's here, right?
Yeah.
Yeah, you make it bigger than. But it's still the same.
Did you guys change the number of steps or something? Maybe someone will think that's how you do it. You wouldn't.
Yeah. Yeah.
Standard that cool. And then just EXP tailors to 1, 2, and 1, 10. And then parentheses, how many times? It's not time. Around this? No.
Oh, so this exports in there. Okay.
Yeah. Time assignment is a function. It's like a different. Really? Yeah.
Yeah, I just want to last question.
Remember, was that another one?
One, two,
How does
Good question. So on the project, the last question, the function is what time is the function?
Yeah.
Because one of the variables you can use are the elements. Step back, to get these curves. Okay, so your T0 as of before we're talking about when this was 1996.
This is so much more.
T0 equals 0 hours. And that was 85.
Yeah, maybe that might be better.
I cannot get that.
80 degrees after 45 minutes. Okay, so then is the T0 going to remain the same here?
That one.
Or is that going to change because is our T0 98.6?
That one is once you have a function, it doesn't change.
So, okay, so the function this
change be like your independent and then your left temperature.
So this T of T here is going to be 98.6. Yeah, it's going to result in a negative time independent. So that the function I have right now, one of the arguments is the independent variable, which is what we're solving for instead. So to redo the function then,
If you want to rearrange it,
Times that you like,
because I can no longer put in time as an argument if I'm trying to solve for time.
This is time.
So would that be a
This is
different
calculation
function?
time.
Or just recreate the function?
that makes sense. There are a lot of
71 nanoseconds.
that solve exactly that problem.
3.9.
I know how to calculate
Not
this,
microseconds.
but I don't know how to calculate the input that's giving me what I want. And there's a function called epsilon.
That right there would make sense, because this would be like
Exactly
expecting
what you're talking about.
essentially this.
Some initial guess, like whatever, 0, and then it's going to iterate, take a look at it.
Gotcha. So the other way, the simplified version is just kind of copy the function, replace the arguments, and solve instead.
Do it by hand
For
and then
T.
manually.
Yeah.
Manually insert the function.
Okay. Thank you.
All right, cool. So we're getting to some cool conversations about like convergence. So I'll redo my Euler integration. So 1900, go to 2021. We'll take steps of 20. Oh, yeah. And then I do want to have So I'm gonna start at I plus 1, and then it's gonna be Euler population of I plus kg times oh. And it would help if I use the right variables that I'm just defined. Oh, -1. There we go. All right, so as I was walking around, we were starting to have some conversations about like the ideas of convergence and kind of what's going on. So right now I have like my Euler integration is integrating every 20 years. And I think for the most part, when I walked around, most people had a general idea, like if I make that smaller, then it does get closer to that red line. So if I go from 20 to 2, then now I've got a lot more circles and they're almost on top of that red line. And what we're showing here is the process of convergence, that we can approximate an exact differential function only using, like I didn't use any calculus in this for loop. I was only saying that the next population is calculating derivative with some math and integrating that way. So that becomes really powerful whenever you start dealing with like nonlinear functions and all the, or like 3-body problems, like all these things that don't have exact solutions. It's just this case we do have an exact solution, so we can look at convergence to an exact analytical function. So the general process is, if you're building a new method, especially if you're in senior design, listen to this because this will impress everyone in your presentation. You demonstrate that your process converges to some result. Then you can show that it converges to like that analytical result. And now you've oh my god, the words just disappeared as soon as I was about to say it and sound really, really great. Never mind. Oh my god. I've said it so many times, I just can't even remember now. Convergence. So we need convergence. Verify. There we go. All right, so we have verified that this integration method works because we have 2 different ways of solving it. Both of them are exactly the same. And the smaller I make time step, the more I can show that yes, in fact, they are exactly the same. There is no difference between by hand calculation versus computer. So I verified the method. The next step would be like validating this method. That I mean, at the year 1900, it's definitely validated because all of them start at the same exact value. So the error is 0. That's not as impressive to say that if I assume the initial condition is something, But if I go out to the year 2020 and report how much error there is, like here, maybe it's an error of 4 or 5%, that validates the method. So I can validate both of the, whether it's by hand or with numerical integration, I have a validated result. So converge, verify, then validate is kind of the general process. If you can, and then from there, you can go on and do like more complicated stuff. Like I verified that my process works, like because I had an exact solution of whatever, a beam bending. Now I want to add, like, instead of a metal beam, I want to look at rubber beams, like huge deflections and stuff. But I know my process is going to work because it worked the first time. Yeah. So first, make sure you converge. Ooh, if I could spell. Then verify. So validation always requires like some outside. Like you can't use a computer to validate itself. You gotta measure. You gotta get out and measure something. And then we hadn't really gone through this. There were like some questions about, like, at least in the last couple of days, how do I figure out like how long it's gonna take for 100,000? And if you try to time it, it's gonna just clock out. Like, it's not going to give you anything, because at some point, whenever you're taking like 1 to the 100,000 divided by 100,000 factorial, it's just it doesn't bother giving you a result. Like, it takes too long. So instead, we'll time it. And I don't need to time like actually making this function. I just want to time how long it takes to run the function. So 1, we'll do 2. One and 10. And then for good measure, why not? Let's do one more. Uh, 50. So when I went from 2 to 10, I did 5 times as many calculations, and it went from, I'll call it 1 microsecond to 3 microseconds. So roughly, I would say if it's 5 times bigger, that it's going to be 1 to 4. Well, I'd say like 4 times this time, just from like a rough estimate. So here I had 1, there I had 4. If I run 50, like multiply by 5 again, I think it's going to be 4 times this, so 16 microseconds. That's my prediction, and we'll see what we get. 16, and instead it's like 38, so it ended up being like 10 times longer. So on a log scale, it's not bad. It's not great, but what I could do is just take these 3 results and extrapolate them. Even with 2 results, I can extrapolate. As long as you have 2 points, you can extrapolate as much as you want. The more points you get, the better the slope you have, but oh, not there. So let's just see what those look like. 0.8, 3.9, and 38.3. Oh yeah, that's my y-axis, and my x-axis is 2, 10, 50. yeah, we can see if I extrapolated 2 to 10, then it'd be a little lower, but it took a little longer because I was going from 10 to 50. Or like, so if I could even use that like lin interp function that we had defined earlier and kind of was troubleshooting for. (100, 1, 2, 3). P1 is going to be 10 and 3.9. P2 is going to be 50 and 38.3. So 86,000 microseconds, so like 90 seconds, at least from those 2 data points extrapolating. Or we could even, again, we can try to like verify this. So at 100 seconds, it should be around 81 microseconds. Just run, has to run. Yeah, and then I get 110. So 80 microseconds, again, on a log scale, basically the same. 10 to the 2, 80, 110, off by a little bit. This, which way is up? That way? Yeah, sometimes it's nano, like, it just tries to give you like 3 decimal places, something like that. Really, it's measuring everything in nanoseconds, but it doesn't report like 816 million nanoseconds. Is it nano? Yeah, I think everything is measured in nanoseconds. Yeah. It depends on it depends on whatever the processor is of this server and like our little Docker container, like how often that clock is sampling and collecting time. Cool. That was all the unsolicited. Well, some of it solicited. A little bit extra. We have like 1 minute. Is there anything else everyone to look at? Oh, the next part? Of like looking at. Yeah. So here, like if I want to say n, let's go from 0 all the way to, I don't know, 30. Don't go too big because it'll just take a long time. And at some point it flattens out, like you get no, yeah, 1 over 30 factorial is already basically 0. And then we'll say like error is going to be zeros and length of n. Oh. So one way that I can calculate this error is like I have NumPy that has exp, and it's a pretty good approximation for exponent, so e to the 1. So I'll compare those two. 1 is my exact value, at least as exact as my computer can store it. And then plot n and error. And if I just put it on a linear scale, it looks like by time I get to 5 in order 5 that there's 0 error. But that's because it's linear. So, and right now it's negative, but it doesn't really matter. All I really care about is like absolute value, like how far away is it? So let me change that. So instead of looking at this on a linear scale of like, I want to look at how much is it changing on a log scale. So I'm going to use semi-log y. So my x-axis is still linear scale, but my y-axis is now, on a log scale. So at first, my error is like about 1, which is pretty bad when I'm trying to approximate a number that's 2. But by the time I get to like 17, at that point, that's where I reached like once you're at like 10 to the negative 15 or 16, you can't do math on that anyway. So that's why it's flattening out, because NumPy and my function have there's no way to get a better difference between the two. Yeah. This one is like super converged. 10 to the negative 11, I'd say is pretty converged. So that I'm not going to measure that. Calipers or something. Cool. Thanks a lot. Thanks.